So after we have the ASC matrix and we have the spline mode, the ASC matrix times the spline mode will give us unsteady aerodynamic pressure, and then we can convert the pressure into forces. Then we can pre-multiply the forces by the transpose of the motion matrix. That will give us the generalized aerodynamic forces called GAF. And once we have GAF, we can establish the Flutter equation. The desired Flutter equation is the P method equation that reads, showing here, where MHH is the generalized mass, KHH is the generalized stiffness, and S is the Laplace variable, and Q infinity is the dynamic pressure, QHH is the GAF in Laplace domain. Then we can define a non-dimensional Laplace parameter called P. P equals to gamma times K for the real part, and the imaginary part is K. So gamma is the decay rate, namely the damping. And so this gives us the P method Flutter equation. Because the inclusion of gamma, the P method can provide accurate gamma in the pre-Flutter condition where gamma, this is the pre-Flutter condition where gamma is negative, and in the post-Flutter condition where gamma is negative. Why we need a non-zero gamma? Of course, the primary interest in Flutter analysis is to search for the flight condition where the gamma is zero, where that is the condition where Flutter occurs. But however, if we have accurate damping in the pre-Flutter condition, we can use that to correlate with the measured damping during flight test. So during flight test, we measure the aerodynamic damping, and if we correlate well with the Flutter solution, then we can base on the Flutter solution to project the Flutter condition. Of course, during the Flutter flight test, we don't want the aircraft go into the Flutter condition. And also in the post-Flutter condition, and we can have the information of regarding to the severity of the Flutter. So if the damping line crosses the zero damping line with a large slope, we call this explosive Flutter. And this explosive Flutter, once it flutters, it may lead to catastrophic structural failure. Okay, so it's very dangerous. However, if when the damping line crosses the zero damping line with a shallow crossing, we know in reality when Flutter occurs and the amplitude of the structural oscillation become larger and larger to a point that because the damping is small and at large amplitude, it may bring in other nonlinearity like a nonlinear aerodynamic effect and nonlinear structural effect. Those effects may limit the growth of the amplitude due to Flutter, so this will give you limit cycle oscillation. So you know if you have this kind of a Flutter mechanism, in reality, when Flutter occurs, the structure may be free from structural failure. Because of the harmonic motion assumption in ZAERO unsteady aerodynamic method, those methods will only give us the GAF in the frequency domain. We do not have the GAF in the Laplace domain. So the Flutter solution, if we based on the frequency domain GAF, is valid only at the stability boundary where gamma is zero. For reliable damping prediction in the complete velocity range of interest, approximation technique for the Flutter solution is required. So we have three methods in ZAERO. The first one is called K method, the second one is called PK method, the third one is called G method. First of all these methods will give you the same Flutter speed. where gamma equals 0. So you will find out when gamma equals 0, all three methods become the same equation. The difference of those three methods is in the the damping value in the pre and post flutter condition. The K method is expressed in the complete frequency domain because we don't have a Laplace domain GF, so we remove the gamma from the equation and end up we have only have the frequency here. Okay, so this is omega square, and we have a GF in the Laplace domain. Then we add a artificial complex social damping in front of the generalized stiffness, and then we can rewrite the dynamic pressure into half rho times omega L divided K squared, because V equals omega L over K, and rho is the density. And then we divided this equation by omega squared. So end up we have this equation, and when lambda is shown here, then we can treat the lambda as an eigenvalue problem. So to solve the K method equation, we have to input a gamma, and then we solve lambda, and then the frequency is 1 over square root of real part of the lambda, and the damping is omega f squared times imaginary part of the eigenvalue. The velocity is the imaginary part of lambda divided by real part of the lambda. So if we have a 4 modes and the size of the matrix is 4 by 4 for given rho, and we get a 4 set of velocity, frequency, and damping, then we change the K value, and then we get another set of frequency, damping, and the velocity. So this is so-called the VG diagram. This is called VF diagram. So for given density, then and given reduced frequency, if we have 4 modes, and we can solve 4 eigenvalues. So we have 4 frequencies, and at a different velocity, and we have 4 set of damping, and then you will plug in different reduced frequency. We have another 4 set of frequency and damping. So we change. So we vary the reduced frequency at a given density. Then we can get a so-called frequency, velocity, and frequency diagram called VF diagram. Also the velocity versus damping, which is called VG diagram. And since the K method numerical procedure requires only a straightforward complex eigenvalue analysis of each reduced frequency, its solution technique is efficient and robust. However, several drawbacks discussed below make the K method a less attractive method for Flutter analysis. And first of all, the solution is only valid at G equals 0. Other non-zero damping values are artificial and may not have significant physical meaning. And the frequency and the velocity are computed at a given pair of the Mach number and the density. This implies that the Flutter boundary computed by the K method generally is not a match point solution. Therefore, because the V is a part of the K method solution, so if you for given a Mach number and air density, the velocity is simply Mach number times sphere sum, but this velocity may not be the same as the Mach number times sphere sum. So it's not a match point solution. So the match point solution can be achieved only by performing a Flutter analysis at various air density iteratively until the condition V equal to m times sphere sum is satisfied. So sometimes the frequency and damping value loop around itself and give you a multiple frequency and the damping as a function of velocity. For example, showing here, for this damping, you loop back. So that means at this velocity, you have more than one solution. So this gives difficulty in tracking the eigenvalue in the reduced frequency list. And worst of all, because this is k in the denominator, so the term 1 over k indicates that k method cannot generate the Flutter solution at k equals 0. This is the reason why the k method excludes the rigid body mode from its Flutter equation, because the rigid body mode, the natural frequency of the rigid body mode is 0, and so you must exclude the rigid body mode from the k method, and the failure at k equals 0 also implies that the k method cannot directly predict the divergence speed instability, and this is an important aeroelastic instability problem. So when normally the divergence speed instability occurs, the frequency drops to 0. This is the reason, because the 1 over k term, the k method cannot directly give you the divergence speed instability. And the next method is pk method. The pk methods they, because we don't have the Laplace domain GAF, so we write the frequency domain GAF here, and rather modify the pk method by adding a aerodynamic damping matrix. So in this pk method, first we split the complex GAF in the frequency domain into the real part and plus I times the imaginary part. Okay, then we can write the so we put the real part here times the dynamic pressure, and we write the imaginary part here and divide by k and times p, because p equals gamma times k plus ik. Okay, when gamma is equals 0, then this k and this k cancel out. So this equation will go back to this equation. But however, when gamma is not 0, then you will find out rather than add additional aerodynamic damping matrix to this equation and give you this modified pk equation. And how do we solve this equation? And the pk solution is obtained by an iterative procedure. So you plug a reduced frequency into this GAF, and you solve p as an eigenvalue problem. If the imaginary part of p, which is reduced frequency, match with the given frequency, then you find a solution. Okay, so this requires an iterative procedure. And the pk method, yes, will behave Vg and Vf diagram without loop problem. So the procedure is that you give a velocity, you have 4 modes, and the pk method will give you 4 set of damping, 4 set of frequency, and then you change it to another velocity, you give you another 4 set of damping and frequency. Then you can connect those damping and connect those frequency to generate the Vg and Vf diagram. The pk method produce result directly for given velocity value of velocity and density pairs. This allows the pk method to provide the match point solution if the given velocity and density pair itself satisfies this equation. So you can get the match point solution from the pk method. Another significant advantage of pk method over the k method is the predictability of the divergence speed, where the frequency of elastic mode becomes 0. So showing here, this is the solution from the K method, and this solution from the PK method. So you can see one of the frequency, one of the mode, the frequency dropped to 0, but you will never reach 0 because of the 1 over K term in the K method equation. And the damping line, when you approach to 0 damping line, you will never cross the 0 damping line. So numerically, the K method cannot predict the divergence. However, graphically, you can tell this is a divergence instability. And but if you look at the PK method, when the frequency of a mode drop to 0, it can drop exactly 0. And then if you look at the damping line, it can cross the 0 damping line. Therefore, numerically, the PK method can capture the divergence instability. However, the added damping matrix into this equation to come out of this modified PK method, this add damping matrix has no solid theoretical foundation, and therefore we developed the G method. The basic premise of the G method lies in the assumed existence of an analytic function of Laplace domain GAF, and P equal to G plus IK. G is the damping, K is the reduced frequency in the domain of G greater or equal to 0 and G less than 0. This premise is based on the fact that Laplace transform of the time domain unsteady aerodynamics for divergence, and when the G greater than 0 and the constant amplitude when G is 0 is analytic. Due to the analytic continuation, the Laplace domain GAF is also analytic for decay motion, so where G is less than 0. Therefore, the Laplace domain GAF can be expanded along the imaginary axis from the G equals to 0 by small g by means of a damping perturbation method. So we can apply the Taylor's expansion for small g, and this will equal to the frequency domain GAF plus the g times the partial g, partial q, partial g. However, because we don't have a partial q, partial g, and because we all we have is the frequency domain GAF, however, if the Laplace domain GAF is analytic, it must satisfy the Cauchy-Riemann equation. This is the Cauchy-Riemann equation. If you combine those equations, you'll find out the partial q, partial g equals to partial q by partial ik. This implies the slope of the GAF along the damping axis is equal to the slope of the GAF along the frequency axis. So we can replace this term by this term. So we have this Laplace domain GAF. Then we can plug this guy back to the P equation, and then we can come out a G method Flutter equation where A, B, C are shown here. And if we treat G as eigenvalue, and because this is a second order eigenvalue problem, and we can convert into a second order, first order eigenvalue problem, and then we solve G as eigenvalue. So if we have n number of modes, and that could lead to 2 times n eigenvalue. So if you have 4 modes, and each time when you perform eigenvalue analysis, you can get a set of G. The G method equation is solved by a reduced frequency sweep technique because we are looking for the imaginary part of the damping to be 0. So we won't have a real damping. And so you first plug in k equals 0, and you have 4 modes. It will give us a 4 set of imaginary part of damping, and 4 set, 8 set of real part of damping, 8 set of imaginary part of damping. Then we change it to another reduced frequency, and we monitor the damping line of the imaginary damping. When this damping line crosses the 0 damping line, and then we find a solution. So at this reduced frequency, the corresponding damping is the real part of damping is the true damping, and then the corresponding frequency is the flutter frequency. So we if we have and when, however, if the maximum reduced frequency in the MK Aero Z car is 0.4, and when we are looking for at least 4 roots, and up to this point, the G method only find 3 roots, so it knows it's short of 1 root. So it will perform extrapolation, and then you will extrapolate the damping line to find the 0 imaginary part of damping condition, and therefore find the real part of damping, and also the corresponding reduced frequency. And somehow the imaginary part of the damping line versus frequency always a straight line. So this extrapolation is very accurate. And for n structure mode, the PK method and K method normally only give you n roots of the Flutter equation, whereas the G method potentially give you more than n roots. For instance, if the exact Theodosian function is used, the number of aerodynamic lag root that could appear is infinite. So this extra root is called aerodynamic lag root. The importance of the aerodynamic lag root becomes apparent when divergence occurs. Because the G method is derived from the Cauchy-Riemann equations, so it's rigorously derived using the Cauchy-Riemann equations, whereas the added damping matrix in the PK method has no solid theoretical foundation. It can be shown that the PK method is valid only when K is 0 or G is 0, or the frequency domain GF is a straight line. Therefore, the derivative is constant. And only at this condition, the PK method becomes and the G method equation become the same. And what's the difference between the PK method Flutter solution and the G method Flutter solution? We found that usually, I would say 98% of chance they will be identical. However, in a few cases, they show a difference in the VF diagram, and this showing here is a 2D incompressible, the 2D airfoil in incompressible flow, and structurally this point is attached to another grid point, and this grid point is can be freely moving up and down. So this gives us a rigid body mode, and also this point is connected to this point by a linear spring. So this gives us a plunging mode, and also connected by a torsional spring. So it gives a torsional mode. So this gives us 3 modes. One is a rigid body. One is elastic plunging mode. Another is elastic torsion mode. So you can see we have a 3 set of because it is incompressible flow and 2D incompressible flow, we have the exact unstable aerodynamic solution in Laplace domain by the Theodosian function, and we can generate the so-called transient method, which is a reference solution shown by the solid line, and the PK method solution is shown by the open symbols, and the G method solution is shown by the solid symbols, where the clouds is the aerodynamic lag root. Okay, this is lag root 1, level 2, and we have 3 rules for the 3 structure modes. And then you can look at, because you have a rigid body mode, and at 0 speed, and the frequency is 0. But as the speed increase, this frequency line could take off from the 0 frequency line and coupled with the plunge elastic mode, and that forms a divergence instability. So, but if you look at the VG diagram, all 3 methods, I mean the PK method and G method, both agree with the transient method well. And however, in the PK method, this rigid body mode frequency remain 0, whereas the aerodynamic lag rule generated by the G method and agree with the transient method. So the inclusion of aerodynamic rules could provide important physics insight of the Flutter solution. The result of the G method suggests that the divergence speed is caused by the coupling of the structural modes and the aerodynamic lag rule, and should be considered as a special case of Flutter instability. When divergence instability occurs on a free structure, the frequency of the aerodynamic lag rule could be no longer 0 and coupled with the elastic mode, resulting divergence. So if you have a free structure, when divergence occurs, and the frequency may not be exactly 0. And if you have clamped structure, and when divergence occurs, the frequency is exactly 0. Section 7. Bulk data card input for Flutter analysis. And this slide lists out all the input cards for Flutter analysis. The most important card is called Flutter, and so this Flutter card is referred to by a case control command called Flutter, and equal to an integer, and this integer refers to the ID of the Flutter card. Also, it can refer to the FlutFast card, and the Flutter card refers to one of these 4 cards. 2 cards are for the match point Flutter analysis. 2 cards are for the non-match point Flutter analysis. And all these cards refer to a MK LZ card, and to grab the Mach number and generalize aerodynamic forces to establish the Flutter equation. And it also refer to a FlutTF card. In this card, you can specify a second order transfer function, and this transfer function will add to the Flutter equation. The Flutter, in the Flutter card, you also can refer to TAB-DMP1 card to list out the modal damping as a function of natural frequencies. And also it refers to a count name list card. In the count name list card, you list out the ID of a count name 1, count name 2 card, and those 2 cards are identical to the next strand card, and to define a 6x6 mass matrix. This is called mass perturbation method. And then the Flutter module will compute to modify the generalized mass matrix using this count name 1 and count name 2. And also, it refers to a set 1 card. In the set 1 card, you list out the index of the modes, which you want to remove them from the Flutter analysis. Also, the Flutter card refer to a flat card, and in this card, you can generate the Flutter mode animation file, and then you can look at the Flutter modes. And also, if you want to do sensitivity analysis of the Flutter analysis, and then you use the FlutSense card. this is the sample Flutter input deck. So you have a Flutter car. The ID is referred to by the Flutter case control command. And then you specify what kind of mode. You have anti, or symmetric, or asymmetric modes. And this one, in this case, refers to the fixed MATM car. And then you say, okay, I want 15 modes to be included in this Flutter analysis. For example, if the assign Fvm executive control command imports, say, 30 modes, then you use say 15. That means you only include the first mode to the 15th mode for Flutter analysis. And this mlist will refer to the set1 car. And then you say, I want also, in addition to the delete mode, I want delete the first mode, second mode, and the third mode. So end up you only have 12 modes for the Flutter analysis. So we have a Flutter car, and it refers to 2 match point Flutter analysis car and 2 non-match match point Flutter analysis car, and then you have a fast car, which is fast but less robust G method, and you have flat param car, and to perform parametric Flutter analysis. Flat asim car, you want to perform asymmetric Flutter analysis by using half-span structure and aerodynamic models. You have flat sync car to perform Flutter sensitivity. So this the Flutter car, and it can be referred to by the Flutter case control command, or you can refer to by the ASC car to do ASC analysis, or refer to by the dynamic loads analysis. And this ID can be negative. Recently, we add a PK method option. The Flutter module, usually if it's positive, you use the G method to solve the Flutter equation. If you put a negative sign in this ID, you're gonna use the PK method to solve the Flutter equation. As syn, either syn, anti, or asyn. This is for symmetric boundary condition mode. This is anti-symmetric modes. This is asymmetric modes. And also you can add a character in the this 4 characters. If it's blank, you use a QB spline for the interpolation of the generalized aerodynamic forces, because you only in the MK Aero Z car, you only list out a few reduced frequencies, but to perform the frequency sweep technique, the G method and the PK method needs to interpolate the GAF from those computed by the MK Aero Z car. This interpolation scheme, if it's blank, is for QB spline. If you add L, it's a linear interpolation. If you add P, it's a second order polynomial interpolation. If you put an integer, and it's a hybrid QB spline and a linear interpolation scheme. This entry fix refers to one of this card, and N modes, you define number of structural modes used in the Flutter analysis. If 0, and all the structural modes are used for Flutter analysis. And so if the assign Fvm equals executive control command imports 50 modes, then in this case you use all 50 modes. If you put N mode equals 0, and this refers to a TAB DMP1 Bohia car, and in this car you specify the modal damping as a function of natural frequencies. And this entry refers to set 1 or set add car list out the index of modes, and those modes will be removed from the Flutter analysis. And this entry refers to a command list car, and the command list car further refers to a command 1 or command 2 car for mass perturbation. And the NK step, the default is 25. It's a number of reduced frequency steps for the reduced frequency sweep technique of the G method and the PK method. If the Flutter car refers to the fixed HATM, this is the match point Flutter analysis. So this car tries to simulate the flight test condition. So usually when we perform the Flutter flight test at a constant altitude, the aircraft accelerates from the low speed to high speed. So you specify altitude, and you specify the mass and length unit, because this unit can be different from those defined in the Aero car. For example, in the Aero car, the length unit is in inch, and here, if you say it's a FT, then the altitude will be in foot, and all the output Flutter velocity will be in foot, and this is a reference velocity. So the Flutter velocity will be normalized by this reference velocity, and the Flut TF is referred to a Flut TF car. In this car, you can add a second order transfer function into the Flutter equation, and then you list out a set of MK Aero car. And for example, in the first MK Aero car is at Mach 0.7, 0.8, 0.9, 0.95, 1.05, 1.1, and 1.2. So in the VG and VF diagram, you can plot the damping of each mode as a function of Mach number, the frequency as a function of Mach number, and then you can see this damping line cross the zero damping line at the Mach number 0.92. So if I say the altitude as 5,000 feet, then that means the aircraft going to flutter at 5,000 feet and at Mach number 0.92. Since this method needs to compute several AICs for the given Mach numbers, this method is very computationally intensive. So it needs to compute AIC at many Mach numbers. Second one, fixed Mach, is a non-match point Flutter analysis, and so this IDMK refer to MK Aero car, and also you can change the mass and length unit, and then after that you give a set of velocity and density pairs. And however, if the velocity and density pairs satisfy the V equals Mach number times the speed of sound, and this fixed Mach car, actually you are doing match point Flutter analysis. So this one will plot the damping and the frequency as a function of dynamic pressure, and so you can see it flutters at dynamic pressure of about 90. And fixed MATM is a match point Flutter analysis. So you give this one refer to MK Aero car. After that, you list a set of altitude from low altitude to high altitude, and of course the unit of altitude is defined by the length unit. And this method can be used to simulate a typical Flutter flight test condition where the aircraft flies at a fixed Mach number but with varying altitude. So because it has built-in atmosphere table in this car. So for a given altitude, you can calculate the corresponding velocity and the density at this altitude based on the Mach number. Then you can calculate the dynamic pressure at each altitude, and you can plot the damping with dynamic pressure, frequency with dynamic pressure, and in this case, it flutters at the dynamic pressure 400. Fixed M then is a non-match point flutter analysis. Usually, we use this car to perform flutter analysis for incompressible flow. So in the MKLZ car, the Mach number is 0. Then you give a density and you give a set of velocity. So you can plot damping with velocity and frequency with velocity. And the flat car is a fast G method for flutter analysis because in order to further reduce the computer time, no flutter mode tracking will be performed by the fast car, because the flutter car performs flutter mode tracking and print out the VG and VF diagram in the standard output file, and also it can generate flutter mode animation file. But if so that's a lot of overhead for flutter analysis for the flutter car. But if you use a fast car, those overhead costs will be removed. In addition, the NK step, the default is 10. The flutter car default is 25. Flat car, you can perform sensitivity analysis of flutter, trim, ASC, and gas load. So this one refer to a flutter car, and you can specify ASC gain set. This one refer to a gain set. Both cars specify list of ID of the ASC gain, and then you can compute the sensitivity of the flutter frequency and the flutter speed with respect to this gain. And after that, you list out the label, thick, mass, and stiffness. The label, you just give a name of the design variable, and the thickness is represent the thickness of the membrane element, the area of the rod element, or area moment of inertia of the beam element. So you want the program will calculate the sensitivity of the G-set mass and G-set stiffness with respect to the design variable. And in this entry, it refers to a DMI-G car or assign matrix equal executive control command. And this one, you import the mass matrix in the G-set for element or a group of elements, and this is for stiffness. Plot through car, it generates the flutter animation file, and it can be referred to by the flutter car or ASC car. And so you then M mode is how many which flutter mode you want to generate this flutter animation file, because the flutter module may capture several flutter modes. So this one is the flutter mode index. N time, because the flutter mode has no line. So N time is that within each cycle of oscillation, how many deformed aerodynamic model you want to output, then you can do a flutter mode animation. And max DISP is a fraction of the reference core defined by the REFC entry in the LZ car to define the maximum displacement of the flutter mode. So this one times this one is the maximum displacement of the flutter mode, because the flutter mode has no absolute displacement. Form, it can be tag plot, pattern, and so on. And also we have a new option here. It's called SPCD. And this one does not generate a Flutter mode animation. It generates a natural Bogota class that contains the natural SPCD Bogota class to specify the enforced displacement at all degrees of freedom of the finite element model. So you can plug in this set of SPCD card at each time step. Then you can perform a stress analysis. Then you will find out at which time step where the highest stress region occur. That means if the structure flutters, it's going to break at that region. And this one you give a file name. And so you can do a Flutter animation. You use the flute card. And also we have a flat VG card, which plot the Flutter frequency and damping curves. And this one refer to the Flutter flat ASN and ASC card. And the M mode is that how many modes the damping and the frequency data, how many modes you want to include in this VF diagram file. X-axis you have a option. You can plot the damping and the frequency as a function of Mach number, as a function of density, as a function of dynamic pressure, as a function of altitude, and as a function of a normalized speed, and speed and EQ UV. You want the equivalent L speed defined as V divided by V REF times square root of Flutter density, normalized by the reference density. The reference density is input here, and the reference velocity is specified here. Okay, so and then you give a file name, and if it's a table form equal to table, then you will generate a file like this. So you have the dynamic pressure, the damping of the first mode, second mode, and so on. And here is the dynamic pressure, the frequency of the first mode, second mode, and so on. Then we have a small program called vgplot.exe, and then you can use this code to process to generate the VG and the VF diagram. Section 7.3, Flutter Analysis Guidelines. First, we want to talk about the impact of high reduced frequencies on Flutter solution. First, you do not want to include very high reduced frequency in the MK LZ card. Normally, K equals 2 is sufficient. This because high reduced frequencies requires a very refined aerodynamic panel model to ensure a converged QHH matrix. Because the G method interpolates the QHH during the reduced frequency sweep technique using a qubit spline over all K value listed in the MK LZ card, a non-converged QHH at a high frequency may contaminate the accuracy of the interpolation. So the solution of higher order modes associated with a high reduced frequency can be captured by the G method's extrapolation scheme, even if the high reduced frequency is not included, okay, in the MK LZ card. Showing here, okay, if this mode is a high order mode, high frequency, and in the MK LZ card we only list the highest reduced frequency to be 0.4, and so at this point the G method frequency sweep technique can perform extrapolation to find the roots of this high order mode. This because Flutter occurs usually at a low order mode, not at a high order mode. The inclusion of the high order mode in the Flutter analysis is only to ensure no unexpected coupling between the lower and higher order mode. Therefore, the accuracy of the solution of a higher order mode is not important for predicting the Flutter boundary. That is, the G-method's extrapolation scheme can provide acceptable accuracy of a higher order mode. However, if this extrapolation scheme of G-method is activated, it will print out this warning message. Such a warning message is not critical and simply suggests that the Flutter solution of the last servo mode may not be accurate. Another problem you may encounter is called mode switching problem. So because the two mode, the frequency may switch here, may be the same here, and then the G method may have problem to track the mode. So for example, if this is the bending mode, if this is the torsion mode, at this point the torsion mode all of a sudden become bending mode, and bending mode all of a sudden become torsion mode. And the mode switching does not change the Flutter speed and the frequency at which the damping curve crosses the zero damping line. So the Flutter boundary is not affected by the mode switching. Only the index of the mode is incorrect. But this, however, will not give us a serious problem, because you cannot talk about, say, oh, this Flutter mode is bending mode Flutter, or torsional mode Flutter. This is an incorrect statement, because you have to say this Flutter mode is due to bending and torsion coupling. This mode switching problem can be resolved by specifying small increment of the speed, altitudes, dynamic pressures, at least in those cars, and smaller increment can help the mode sorting scheme to track correct damping and frequency curve of each mode. And also, if you have 5 modes, and all of a sudden you may have a extra rules. This rule is called aerodynamic lag rules. And so you can see if this is the bending mode, and as the speed increase, the frequency drop to 0 at this speed. Meanwhile, at this speed, all of a sudden extra rule appear. This is called aerodynamic lag rule. This lag rule satisfies the Flutter equation, therefore it's a true Flutter solution. It occurs only when the frequency of an elastic mode drops to 0 and to the real axis in the negative real axis in the locus diagram. Because the generalized aerodynamic forces has a branch cut along the negative real axis, the 0 frequency elastic mode coupled with the branch cut resulting 2 rules. One of the 0 frequency elastic mode, and one called aerodynamic lag rule. The aerodynamic lag rule could be either stable or unstable. Unstable aerodynamic lag rule occurs usually due to the divergence problem. The frequency of the aerodynamic lag rule may not be 0 if the structure has a rigid body mode. The divergence problem with a non-zero frequency is called dynamic divergence. So whenever you have a rigid body mode and the divergence problem occur, the frequency may not be 0. If you have a clamped wing, say you are doing the wind tunnel testing, and you have a clamped wing, once the divergence occur, the frequency is 0. But if you have rigid body mode or for the free structure, the frequency may not be exactly 0. Thus, because when the divergence occurs, you will create a lift. This lift will move the whole aircraft up and down. Because the whole aircraft, the mass is huge, therefore associated frequency is small, but not 0. And where did this branch cut come from? We can use the exact Laplace domain 2D incompressible Fvm function. This is the Fvm function. S is the Laplace variable. And if we add a very small reduced frequency, then we can see the Fvm function contains a function called Arctangent function. And if the G is greater than 0, and for both very small positive k and very small negative k, this arctangent gives us 0. However, if g is negative and if the k is positive, it gives us pi. But if k is a small negative, it gives us a negative pi. So you have discontinuity here, and if you're approaching from the positive k and approaching from the negative k, and when they meet here, they have a discontinuity. So this shows that the QHH in the Laplace domain has a discontinuity along the negative real axis, the branch curve. We call it this branch curve. So if you look at in the frequency domain where the g is 0, the real part of the Theodosian function is symmetric between the negative k domain and positive k domain, but its imaginary part is anti-symmetric between the negative k and positive k domains. If along the negative g-axis, the imaginary part of Theodosian function is discontinuous from the small positive k to the small negative k. So this is a branch curve. Okay, and what's the impact of the branch curve to the Flutter solution? If the Flutter equation is also solved in the negative frequency domain, the Flutter solution in the negative and positive frequency domain are symmetric about the g axis. Okay, so if we solve the Flutter equation in the negative frequency domain, it will be a mirror image of the positive k domain about the g axis. So this can be shown by the pk method. This is the pk method. So if the k is positive, then QH equal to the real part plus I times imaginary part. If we plug in the negative k, and this will become the real part is the same, but imaginary part switches sign. However, we have this term because this imaginary part q divided by k, and give us back the imaginary part divided by k. So it is the same as the negative frequency domain Flutter equation is the same as the equation in the positive frequency domain. Therefore, you have their mirror image. Since p equal to g plus ik in the positive, and p equals g minus ik in the negative frequency domain, the Flutter solution in the negative frequency domain are the mirror image about the g-axis of those in the positive frequency domain. However, one exception: when the divergence occurs, and this diverging mode from the negative frequency domain all of a sudden become 0. So it appears in the positive frequency domain. So all of a sudden you have one extra root. Okay. So when the diverging instability occurs at k equals 0, both solutions from the positive and negative frequency domains meet at the negative g-axis. The diverging solution from the negative frequency domain at k equals 0 become an extra root, a sudden appearance, okay, in the positive frequency domain called aerodynamic left root. Because of the branch curve, one of these two roots, one from the positive and the other from the negative frequency domains, become positive g unstable, and the other one become negative g, which is stable. And the next one we want to talk about the influence of underwing stall aerodynamics on Flutter. And the aircraft with the stall configurations requires an extensive effort to model all the stalls in the aerodynamic model. So sometimes we want to say, okay, some of the stall, if they have little impact on the Flutter solution, we do not need to include them in the aerodynamic model. This because the units of generalized aerodynamic forces matrix involved in the Flutter equation are in work done as force times displacement. So therefore, any stall and launcher at which a large displacement in the Flutter mode occurs must be included in the in the aerodynamic model. So let's give you an example. So this is the aircraft with a fuel tank and air-to-ground missile and M9P missile and the tip launcher. The tip launcher is modeled by a ZAERO 7, and then we keep the structural model with all stores to be invariant. Okay, then we only the aerodynamic model changes. So if we include all the underwing store and tip missile in the aerodynamic model, and we get a Flutter solution like this, so we call this a reference solution. Next one, if we take out the fuel tank from the aerodynamic model, and the error of a Flutter solution is only 4%. If we take out the air-to-ground missile, the Flutter solution, the error is 8.6%. If we take out both fuel tank and air-to-ground missile, the error is 3%. If we take out the fuel tank and then we take out the M9P missile, we all of a sudden we have 20% of error. If we take out air-to-ground and this M9 missile, the error is 6%. And if we only take out the M9P missile, the error is 15%. If we only take all of that, we only keep the tip launcher here, we have 10% of error. Now, if we further take out the launcher from the aerodynamic model, all of a sudden we have no flutter. So this tells us even the tip launcher is modeled by the ZAERO 7. It's a small pieces. Its area is small, but since once the flutter occurred, the flutter mode of the wing has the largest displacement at the wing tip. So this force times this large displacement it will give us it will give a big contribution to the generalized aerodynamic forces. So if you don't model the tip launcher, you get a completely wrong solution. So any aerodynamic component near the wing tip have large influence on flutter solution, since the wing tip has the largest displacement in the flutter mode. And in the flutter analysis, it refers to say fixed ATM, and this will refer to the MK car, and from the Mach number and from the method, you will select a corresponding aerodynamic method to generate the AIC and the generalized aerodynamic forces. And the typical this is a typical Flutter output in the standard output file. And for example, you have 4 modes, and then this is modal damping, which is input by the TAB DMP1 bolt.com. And then you will list out the damping frequency and the reduced frequency of each mode as a function of normalized velocity, density, and altitude. Then you will further look for the zero damping condition, and it will tell you at this condition what's the flutter altitude, flutter speed, and the normalized flutter speed and the flutter frequency, and flutter dynamic pressure, flutter density. So in addition to this modal damping specified by the TAB DMP1 car, the Flutter module will further add some structural damping from 0.5% to 4%. So it's say if you have one additional structural damping, this is your Flutter solution. And sometimes you will see this region is blank. Once you have a blank region here, that means if you add beyond 2.5%, there's no crossing. The damping line will not cross at 2.5%. So that means the damping line only cross at 2%. That means this Flutter mode is a hump mode, because the damping, the largest unstable damping, is only only bigger than 2% damping, but less than 2.5% of damping. And after you print out this table, you will do a flutter conformation to. So this the flutter frequency, this is flutter velocity from this table. Then you will plug those two values back to the flutter equation, and then you will use the dynamic pressure as an eigenvalue problem. So you will compute the eigenvalue of the dynamic pressure. You will compare to the interpolated dynamic pressure. If the error is too large, then this flutter solution may not be a realistic one and may be caused by the inaccurate interpolation of the QHH. That means you have a non-converged QHH at a high reduced frequency. And next, you will do flutter mode tracking. The mode with a large percentage are the dominant mode in the flutter mechanism. So usually you will find that the biggest contributing mode is labeled as 100. And next one is decimal. And the rest of the mode contribution is very small. This means that this mode is flutter is caused by the coupling of the mode 1 and the mode 2. And also it means if you take out those natural mode from the flutter analysis, you will get a very similar flutter solution. So at the end, you can do get a flutter altitude, speed, frequency, dynamic pressure. Then you can use a plot fluid car to animate the flutter mode, and you can use plot VG car to generate the VG and the VF diagram. Section 7.4. Mass increment method for rapid flutter analysis of massive aircraft store configurations. The parametric flutter analysis, you use the mass increment method for massive flutter analyses of an open or closed loop system with various mass and stiffness distribution in the structure. And the data mining the massive flutter results by automatically searching for the velocity damping curves crossing at a user specified damping level. And the Fvm module can output a summarized flutter result in table form to ASCII file, and so you can you use the off-the-shelf graphic tool such as TechPlot for the post-processing, and also it will output flags to indicate the severity of the flutter instability. For a fighter wing, for a fighter aircraft, if you have fully loaded store configuration, and if you drop store one by one, you will find out the possible combination of the store configurations is about 400. So if you have many fully loaded store configurations, and you need about 5,000 flutter analyses, and just by looking at the result of each flutter case, it could take a lot of time, not mention the large computational time. And so the Fvm car module can perform thousands flutter analysis of each aircraft with the store configuration in one single computation. And then you will output a summarized flutter result in the table form. Okay, so you can easily look at the flutter solution of each store case. So this mass increment method can be shown by this equation, where MB and KB are the mass, GSAT mass and stiffness matrices of the baseline structure, and delta M, delta K are the incremental change of mass and stiffness from the baseline structure to the ith structure of interest. So those represents the mass and the stiffness of the ith store. and so the store conversion can be thousands. And if you use the direct method, and then for each aircraft store configurations, you have performed eigenvalue analysis, and then you get the mode. From the mode, you can calculate the generalized mass and the stiffness and the aerodynamic forces. Then we assume we use the modal approach, and we can construct a Flutter equation. So for the direct method, you have to repeat these cases n times. For the mass increment method, we first we take out the underwing store, and so we use the baseline mode of the clean wing configuration. Then we construct the generalized mass, stiffness, and aerodynamic forces, and then we assume use the baseline mode, and then we can generate the generalized mass and stiffness of the store. We add into the Flutter equation, then we can solve this equation. So comparing this and the direct method and mass increment method, and we only need to generate perform the modal analysis once, and then we can internally add the generalized mass and the stiffness due to the store, and one by one. Mass increment method assumes that the Flutter modes in the physical coordinate x can be superimposed by the baseline mode. However, for aircraft with a heavy store, x may contain a local deformation at the wing store juncture. So the baseline mode should contain a mode that has a similar local deformation. So this suggests that the baseline structure mode structure should be the one with the heaviest store. So this mass increment method actually should be called mass decrement method. So we take out the heaviest store from the generalized mass matrix. Then we add the generalized mass matrix of ith store in here, and then we can then this generalized mass and generalized stiffness matrix are no longer diagonal. Okay, but nobody said that we have to have the diagonal generalized mass and stiffness matrices in the Flutter equation. So, however, to perform the flat parameter analysis, we may need a lot of modes. If only the lower order mode, for example, we have 30 modes, are included, the natural frequency computed by the mass increment method may appear in two groups. The natural frequencies in the low frequency group are practically identical to those of the direct method. The high frequency group does not represent the actual natural frequencies. It corresponds to the synthesis mode in the vicinity of the incremental mass and stiffness. So this problem can be resolved by renormalizing the Flutter equation using large number of modes. For example, we have 100 modes. And first we solve the eigenvalue problem, and we obtain the eigenvector. Then we pre and post multiply this generalized mass and stiffness and the generalized area and forces by this eigenvector. And so this matrix, those two matrices become a diagonal. And once they become diagonal, we can truncate the mode. For example, we take out the last 70 mode. So end up we only have a 30 modes in the Flutter equation. And give you one example. If we have a store attached here, then the store has three different inertias and three different weights. So this is the heaviest store. This is the lightest store. Now, if we use the heaviest store mode as a baseline mode, and if we want to compute the natural frequencies of the lightest store, and we can compare the direct method with the mass increment method, and you can find that all the natural frequencies are practically the same. The largest error is only about 0.22%. However, if we use the lightest structure lattice store structure as the baseline mode, then we want to compute the natural frequencies of the heaviest store, then we may have a very large error. So this proved that if we want to perform the Flutter param analysis, you have to use the fully loaded store configuration as the baseline mode, and then you include a lot of mode. Then in the Flutter param car, you take out some modes. And the Flutter solution is shown here for Mach 0.9, and this is direct. This is the mass increment for all the store weights. And you can see that the error is very small, and this is the Flutter frequency. Also, the error is very small, and this at the Mach 1.2, and also the error are very small. And if we look at the VG and the VF diagram, this is from the direct, this is from the mass increment, and at the Mach 0.9, at the 1.2 for the symmetric modes, and this is anti-symmetric. You can compare the VG and VF diagram between the direct method and the mass increment method. They are practically the same. And also, you will output a summarized Flutter solution table, and then you can generate a Flutter speed contour in terms of pitch inertia and weight. And also, we validate this mass increment method with the next-gen solution. If we look at this case, if we use the direct method, we have 288 cases, then times two boundary conditions, the symmetric and anti-symmetric conditions. Each case, an takes about 103 seconds. So the total time is 16.5 hours. Okay, even you have a saved AIC matrix, ZAERO reads the AIC back, and for each time it takes about 324 seconds. So end up you have a 26 hours just by reading the AIC back. So if you look at the mass increment method, you only need to perform the national analysis once, and ZAERO only need to read the AIC back once. So the amount of saving is about 42.5 hours. Of course, to solve the Flutter equation, they are almost the same. And so this is the car called Flutter param car, and this ID is referred to by a Flutter param case control command, and this refers to a Flutter car. In the Flutter car, you can use the entry mlist to delete the mode, and you give a file name here to store the summarized Flutter solution table, and this reference density is used to define the equivalent L speed, and this error lag yes or no. If it's a yes, that you consider the aerodynamic lag rule as a part of the Flutter solution. The default is no. This confirm is yes or no. If it's yes, the Flutter param module will perform a Flutter confirmation to make sure this Flutter mode is a true Flutter mode. And after that, you specify flag A, flag B, flag C, and flag 0 using characters. And then you specify three setup for damping level. For example, GA 0%, GB 1%, GC 2%. So, if the damping curve cross 2% of damping, and this flag will appear in the summary table. If the damping curve cross 1%, but it does not cross 2%, this flag will appear. If the damping curve cross 0%, but it does not cross the 1%, this flag will appear. If there's no flutter, and this flag 0 will appear. And in this case, the flutter frequency, the default is negative 9,999 Hertz. And this is an open-ended card. And this one refers to a countname list card. And the countname list card refers to a countname 1 or countname 2 card. And then you take out this mass defined in the countname 1 and countname 2 card. If the countname 2, countname 1 card use the store is in weight, then you have to convert them into mass unit. And so this is the sample output of the Flutter summarized table, and it give you the Flutter speed and Flutter frequency, and this case shows that the Flutter damping curve cross 2% of damping for mode 2, and this case shows the no flutter, and this case shows it crosses 0% damping, but it does not cross 1% damping, and this case shows it crosses the 1% damping, but it does not cross the 2% of damping line. And then after that, you will output say if you add 2% of damping, this is the Flutter solution. If you add 1% of damping, this is the Flutter solution. If you add 0% of the damping, this is the Flutter solution. Okay, as we mentioned before, if the basic assumption of this Fvm approach is that the ASC remains the same. That means if you have a aircraft with a source, you do not include those store in the aerodynamic model, okay? Because we assume the underwing store influence to the flutter result is small. However, if you have any aerodynamic component attached to the wing tip, as we shown before, any aerodynamic component attached to the wing tip may have a large influence in the flutter solution. So for a fighter aircraft, you may have a wingtip missile, and sometimes you may not have a wingtip missile. So you have to generate two sets of aerodynamic model. So you have two sets of ASC matrix, and all the underwing store are not modeled aerodynamically. But the tip missile, if you have tip missile on wing tip, you have to model them in the aero model. Okay. So this okay. The next module is called FlutASym. The FlutASym module is for flutter analysis of aircraft with the asymmetric store configuration using a half-span model. And to perform the flutter analysis of asymmetric store cases usually requires a full span structure model. First, you want to generate a clean wing full span structure model. Then you attach the asymmetric store to the right hand side wing and to the left hand side wing to construct an asymmetric structure model. However, expanding a half-span structure model to a full-span structure model is by no means a trivial task. if the structural model is complex and involves the mass and stiffness and degrees of freedom being defined in the local coordinate system. So if you only have a half-span model, if you want to do a full-span asymmetric Flutter analysis, to expand the half-span structural model to a full-span structural model may be a tedious job. Okay, so performing a Flutter analysis of full-span model implies that the problem size of the structural and aerodynamic analysis is increased by a factor of 2. And also, therefore, is highly desirable that a Flutter solution of aircraft with asymmetric store configuration be obtained using only a half-span structural model and aero model. Okay, so we start out with a clean wing full-span model. That means we have no store, and so this is the Flutter equation, and where the AIC is the aerodynamic influence coefficient matrix, and RR is the right-hand side panel influence to the right-hand side panel. LR means left-hand side panel influence to the right-hand side panel. RL means right-hand side panel influence to the left-hand side panel. LL means the left-hand side panel influence to the left-hand side panels. Because of no store, both structural and aerodynamic model are symmetric of the center line of the fuselage. So the G-set mass matrix on the right-hand side equals to the left-hand side, and also the stiffness matrix on the right-hand side equals to the left-hand side, and AIC RR equals AIC LL, and AIC RL equals to AIC LR. Then we assume the structural deformation X to be a linear combination of the symmetric and anti-symmetric mode. So if we only have a half-span model, then we can generate a symmetric mode, an anti-symmetric mode, and we construct a full-span mode. As because the symmetric mode, so right-hand side equals to left-hand side, and because of the anti-symmetric mode, we put a negative sign here. Then we plug this equation back to that equation, and then we pre-multiply that equation by this motion matrix, and we end up with this equation, and the MSS is the generalized mass of the symmetric mode. MAA is the generalized mass matrix of the anti-symmetric mode, and this is the symmetric generalized stiffness. This is anti-symmetric generalized stiffness matrix, and the QSS is generated by pre and post multiply this matrix by the symmetric mode, and where AIC RR plus AIC RL is called symmetric AIC matrix, and this is called anti-symmetric AIC matrix. So this confirms that for a symmetric configuration, the Flutter analysis requires only a half-span model. So you use the half-span model, and you generate a symmetric mode and anti-symmetric mode, and you generate a symmetric AIC and anti-symmetric AIC. Then you can perform a symmetric Flutter analysis and an anti-symmetric Flutter analysis. Now, if you have an asymmetric store configuration, and then you add a delta MR, which is the right-hand side store mass, and delta ML, which is the left-hand side store mass, and this is the stiffness of the right-hand side and left-hand side. Then because we do not model the underwing store aerodynamically, so the AIC is the same. Okay, because of the asymmetric structure, the physical deformation is also asymmetric. So either symmetric nor anti-symmetric about the center line of the fuselage. However, X can be still represented by the combination of symmetric and anti-symmetric mode if sufficient number of modes are given. So we still can use this equation, and we plug this equation into here, and we pre-multiply by transpose of this motion matrix. We come out a Flutter equation something like this. So all the term, the delta MR SS is a generalized mass matrix of the store on the for the symmetric mode, and all those terms can be computed internally in the Fvm module. So you don't need to perform full span structural analysis. And using half-span structure model, the symmetric and anti-symmetric modal solution can be generated by imposing the symmetric and anti-symmetric boundary conditions along the center line of the fuselage. And so all the generalized mass, stiffness, and modes can be obtained, and we can use the symmetric mode and anti-symmetric modes. The unsteady aerodynamic method, such as zone 6, zone 7, can generate the symmetric generalized aerodynamic forces and anti-symmetric generalized aerodynamic forces. All the generalized incremental mass and stiffness matrix due to the store can be calculated without performing a finite element analysis. As all terms in the Flutter equation in the generalized coordinates are obtainable using only a half-span model, so the Flutter solution can be calculated using either the K method or the G method. So the car is called Fvm, and this is ID. This ID is referred to by Fvm case control command, and this refers to a fixed HATM of fixed MDAM cars, and this is how many modes you want to keep in this Flutter analysis. So if the total number of modes of Fvm is the number of structure modes plus plus the number of the anti-symmetric mode, and this refers to a TABDMP1 car to include the structural damping in the analysis. MList refers to a set1 car to list out the mode to be deleted from this Flutter analysis. And content list refers to a content list car. NK step is the frequency steps used for the reduced frequency sweep technique in the G method, and this is referred to the right hand side store mass. You want to take it out or you want to add in. This is for the left hand side. So a typical application using the Fvm Bogota car is the Flutter analysis for aircraft with asymmetric store configuration, and such as the showing here. So this store and this store, they are asymmetric. So if both store 1 and store 2 are not modeled aerodynamically, by assuming the store aerodynamic influence is small, then the asymmetric store effect exists only in the structure matrix. So you want to if you only have a half-span model, you want to attach both store 1 and store 2 on this half-span model. Then you generate a symmetric mode and anti-symmetric mode of this structure model. And then you have a Fvm car. It refers to by the Fvm case control command. Then you import the symmetric mode and anti-symmetric mode, and then you can generate the Flutter animation, and the Fvm refers to the fixed ATM, fixed mark, and fixed MDAM. And then it refers to TABDMP1 car to include the structural damping in the Flutter analysis. Then you refer to the content list. The content list lists out the ID of content 1 and content 2 car. So the select case is called HA144F, and then we first generate a full span structure model, full span aero model. And on the right hand side wing, we have a store mass, a store weight about 3,000 pounds, but on the left hand side, we have three different store weight. One is 0, one is 1,000 pound, 2,000 pound. So this is an asymmetric structure model, and then we use the full span model to generate three sets of a Flutter solution, and we use this Flutter solutions as a reference solutions to validate the half span model. And so we have a half span model. Then we have 3,000 pounds here, and then we generate the symmetric modes and anti-symmetric modes. Also, we have a half span aero model. So we by imposing the symmetric anti-symmetric boundary conditions on the clean wing half span model along the center line, and then we can generate the symmetric and anti-symmetric generate mass and stiffness, and also the modes, and also can generate the symmetric anti-symmetric generate aerodynamic forces. And then we have three sets of mass. So on the left hand side, the first case is 0 pounds, 1,000 pounds, and 2,000 pounds. So we use two assign Fvm executive control command to import the symmetric modes and anti-symmetric modes, and we have three subcases. Each one refers to a flat asym card. And so for the first flat asym card, we want to keep 30 modes, and we want to include some sort of damping. And then the left-hand side, this entry refers to a condemn list. And in this condemn list, it refers to a condemn 2 card. And this condemn 2 card defines a 3,000 pound mass attached to this structure grid. And then in the condemn list, we want to take out this 3,000 pounds. So we put negative 0.999 there. And because this is in pounds, and we have to convert it to a mass unit. So in this case, we convert it to slug. And this is the first case. And second case, we refer to another condemn list. And in this condemn list, we will refer to the same condemn 1 card, but we take out 2,000 pounds. To take out 1,000 pounds. And then we take out, then this case, we take out 1,000 pounds. So first, we want to compare the natural frequencies, and for the three cases, and using the full span model and half span model, you can see in all three cases, the error in natural frequency are very small, and so this confirm this half span model approach. Then we also compare the Flutter solution, and this is the full span model, half span model. This is the Flutter speed. This is the Flutter frequency, and you can see all three cases are compared well between the half span and the full span model approach. And also, this asymmetric store cases can be used for massive number of asymmetric store Flutter analysis. If stores are not modeled aerodynamically, all terms in the Flutter equation is independent of the stores, except the incremental generalized mass and mass matrices of the store. So we have all those matrices can be computed once, and then for each store case, we just compute those terms for each store case, and in this flat asym card. So without performing a finite element analysis. This implies that the Flutter equations of massive number of asymmetric store cases can be rapidly constructed and solved. Only one symmetric and anti-symmetric finite element model analysis of the baseline half-span model is required. On the other hand, The full span model requires the finite element model analysis of each store cases unless the Fvm module is used. And we can use the massive number of Flutter solution for asymmetric store configuration can be rapidly generated. We have another module in ZAERO called Fvm. Okay, this one is performed. It's very similar to Flutter, but for asymmetric store configuration using a half-span model. So the conclusion is that we have developed a asym module to do Flutter analysis for aircraft with asymmetric store configuration, but using only a half-span model. This half-span model approach can practically generate the same Flutter solution as that of the full-span model approach. And the tedious effort in expanding a half-span structure model to a full-span structure model can be avoided. And this half-span model approach can be used as a rapid Flutter screening method to identify the critical Flutter cases among massive number of aircraft with asymmetric store configuration. Section 7.5, using GVT, using ground vibration test GVT data for Flutter analysis. Structural dynamic characteristics predicted by the finite element analysis may not be in good agreement with the GVT result. Therefore, it is desirable to directly use the GVT data for Flutter analysis. The inaccuracy of the finite element result usually is caused by the difficulty in accurately modeling the stiffness of the real structure. However, the mass distribution of the real structure usually can be accurately represented by the finite element model. To construct the Flutter equation shown here requires the generalized mass matrix MHH, which is equal to MGG and pre and post multiplied by the motion matrix. And the generalized stiffness matrix can be computed from the generalized mass matrix and pre-multiplied by the omega n square, and omega n square is a diagonal matrix containing the natural frequencies omega n. And the generalized aerodynamic forces QHH can be computed from the AIC, pre and post multiplied by the motion matrix. So GVT can measure the the natural frequencies and the mode shapes at the accelerometer locations. We call it phi sub GVT. Some GVT technique can measure the generalized mass, but may not be accurate. So the GVT to Fvm module in ZAERO can use the GVT measured natural frequencies and the mode shapes to perform aeroelastic analysis. The input of the GVT to Fvm module are the GVT data and the GSAT mass matrix. The major task of the GVT to Fvm module is to interpolate the GVT measured mode shapes from the accelerometer location phi sub GVT to the grid point of the finite element model phi sub Fvm. So to perform an aeroelastic analysis such as Flutter requires three types of structured data: the generalized mass matrix, the generalized stiffness matrix, and the mode shape at finite element grids. The methodology behind GVT to Fvm module is shown as follows. The mode shape matrix GVT phi sub GVT measured at GVT accelerometer locations can be mapped to the finite element grid point using the spline method, such as the infinite plate spline method, thin plate spline method, and the beam spline method that jointly construct a spline matrix. So once you have a spline matrix, you can multiply to the mode, the GVT measure mode, and you can get the mode at the finite element grid. So it is assumed that the GSAT mass matrix of the finite element model is accurate. So you can calculate the generalized mass matrix and then general stiffness matrix can be calculated from the natural frequencies measured by the GVT, and then also you can calculate the generalized area and forces from the ASC matrix. So you can construct the Flutter equation, and the GVT to FEM depends on the accuracy of the MGG and the spline method. If both are accurate, the generalized mass matrix should have all diagonal terms being much larger than the off-diagonal terms. Then all the off-diagonal terms in the generalized mass matrix can be replaced by zeros, rendering the generalized stiffness matrix is also a diagonal matrix. So the car is called GVT to FEM, and sim can be sim, anti, or asim that match the entry boundary of the assigned FEM equals executive control command, and whose imported model data is replaced by the by those measured by GVT. To activate GVT to FEM, the GSAT mass matrix must be imported by the assigned FEM. Assigned matrix equals executive control command with entry mnam equals mgg. So in case the GVT coordinate is different from the finite element model coordinate, then you need to define a control car to transform the GVT data, the grids to the finite element coordinates. And sometimes if the GVT model is a left hand side wing, the finite element model is the right hand side wing, then you want to use flip to flip the GVT grid to the same side of the finite element model. So you have four choices, and you have XY, XZ, YZ, or blank. XY is the symmetric plane is the XY plane, and XZ is the XZ plane. YZ is the YZ plane. If blank, then they are in the same coordinate. And scale, in case the size of the GVT model is different from the finite element model, so maybe the length unit is different. So you use the scale to convert them to be the same unit. And GVT IMP is an ID of an exe file, and in this car, it specifies the name of the input file on which the GVT data is stored. So mode out is ID of a exe file bought a car to specify the name of an output file on which the mapped GVT measure mode shapes at FVM grids are written in the output format. And in the GVT, sometimes if you want to measure the modes, say along a middle body, and then because then the accelerometer can measure the translational degrees of freedom. But however, if we want to use beam spline, because the beam spline requires the rotational degree of freedom, so you have to somehow create the rotational degree of freedom from the translational degree of freedom. So you refer to this car, and this car is very similar to the SPLNDOF car. Okay, so you relate a dependent degree of freedom at a GVT grid to two other independent degree of freedom at two GVT grid. FEM out is ID of another exe file, car to specify the name of the output file on which the modified FEM model solution output file that is imported by the assigned FEM, the executive control command, will be written. So if you import the NetStream output file, and then in this file you will rewrite the natural output file, except the natural frequencies, the general stiffness and masses, as well as the mode shapes and the Fvm grid are replaced by those GVT. So the user can import this file using the assign Fvm executive control command into another ZAERO job to perform aeroelastic analysis using GVT measured data. This GVT to Fvm is open-ended car. So you have method, Fvm grid, GVT grid, CID, flex, EPS, curve, and plot pen. So for the first method, is a character either 0, beam, IPS, or TPS. If it's 0, that means you assume first of all, this spline is performed using a component by a component approach. So if you have if you have a finite model of the wind tunnel model supporting structure, so those supporting structure should not be included in the generalized mass. So you have to put a 0. So you put a 0 at those Fvm grid to model the wind tunnel model supporting structure. If method is IPS, then you use the infinite plane spline method. If you use beam, you use the beam spline method. If it's TPS, you use the thin plate spline method. The next is a Fvm grid. It is an ID of a set 1 set add car to list a set of a Fvm grid ID involved in the spline. Among all Fvm grids listed by all Fvm grid entry, no duplicate ID can exist. In addition, all Fvm grids must be referred to by all Fvm grid entries only once. So in other words, every Fvm grid ID should appear once in all the Fvm grid set 1 and the set add car. And GVT grid, you again is ID of set 1 and set add. And to list out a set of GVT grid ID involved in this spline. For those GVT grids listed by the same entry Fvm grid, no duplicate ID can exist. However, between different set 1 car, the same GVT grids can be used. Okay, but if method is 0, this entry GVT grid is not used. CID is the ID of a core car. If the method is 0 or TPS, CID is not used. If method is IPS, because the infinite plane spline method needs a spline plane, so the XY plane of the core car is the spline plane. If the beam spline method requires a spline axis, so the Z axis defined by the core car is the spline axis. Flex is usually we put 0. EPS is defined as small tolerance. If two GVT grid points are located within the same tolerance, it becomes a fatal error. And curve is the curvature effect of the beam spline. And plot pen is integer. It is absolute value determines the ID of an exe file data card to specify the name of the output file on which the Fvm grids list in the set 1 car specified by the entry Fvm grids, and the GVT grid list in the set 1 car specified by the GVT grid, except transform in the Fvm coordinate will be written. So this test case is a wind pylon engine nacelle case. And the Fvm model contains about 253 grids, shown by the blue circles, and it has 20 modes. Among those 253 grids, we select only 120 grids, shown by the red circles, and I select treat as GVT grid. The mode shape at those GVT grids are treated as the GVT measure modes. Using the GVT to FEM module, the 20 GVT modes at the 120 GVT grid are split back to the 253 Fvm grid point. The accuracy of the GVT to FEM module can be verified by comparing the spline modes with those directly computed by NetStream, showing that the generalized mass matrix is a nearly diagonal matrix. Finally, comparing the Flutter solution using the NetStream computer model data with that using the GVT to FEM result. So we have a GVT to FEM, and the mode is a symmetric mode, and this one refers to a file. In this file, it contains the GVT measure data. Then we have because we have a winglet and the engine nacelle and the pylon. So we use the infinite place spline method for the wing grid, and this one 1000 and 1010 list the Fvm grid and GVT grid on the wing. And for the winglet, we use a thin plate spline, and 6000 and 6010 is the Fvm grid and GVT grid on the winglet. And for the pylon, it's shown here, and we use IPS. For engine nacelle, we use a TPS. And this is the aerodynamic model. And two sets of mode shapes are generated on the aerodynamic model through the spline module. The fuselage is now moving from the Fvm computer mode called NetStream mode, and from the GVT to FEM generated mode called the GVT to FEM modes. Then we can compare those two sets of modes, and then you can see the spline module did a good job. And then we compute the generalized mass, and by using the GSAT mass pre and post multiply by the phi GVT to FEM, and you can show that the generalized mass is a nearly diagonal matrix. And finally, we want to compare the Flutter solution, and the first set uses the generalized mass and stiffness matrices and the mode shapes directly computed by NetStream. Another one is generated by the GVT to FEM module. So you can compare the VG diagram. They are nearly identical. So this demonstrates the accuracy of the GVT to FEM module for Flutter analysis. If the GSAT mass matrix of the finite element can be accurately represent the mass distribution of the real structure, and sufficient number of accelerometers are used by the GVT so that the GVT measure modes can be accurately splined to the finite element model grid. So the accuracy of the Flutter solution heavily depends on the accuracy of the mode shapes and the natural frequencies predicted by the finite element analysis. The traditional method for improving the accuracy of the finite element result usually is achieved by tuning the stiffness distribution of the finite element model, but simultaneously matching with the GVT measure natural frequencies and the mode shapes for all the critical modes is difficult. This tuning process is usually very tedious. Today, because the mass distribution of the structure can be directly calculated from the CAD model, the GSAT mass matrix is usually accurate. So using the GVT to FEM module, accurate generalized mass matrix can be obtained. Using the GVT measure natural frequencies, accurate generalized stiffness can be obtained, which completely bypass the tuning process of the stiffness distribution of the finite element model. The GVT to FEM module also can be used to determine the optimal number of locations and the numbers of the accelerometers prior to GVT ground vibration test. So by selecting a reduced set of grid points from the finite element model and treat the finite element compute motion as the GVT measure mode. Flutter solution can be obtained by the GVT to FVM module, repeating this process until the GVT to FVM Flutter solution agree with the Flutter solution directly using the finite element compute model data.